So my talks, I'm trying to do two things in this talk. As Abe remarked, one of the jobs that we've set ourselves is to give talks which are not just for each other, that is amongst the physicists, but also to people who are not in the physics world. So I'm going to try and do that. I'm going to try and straddle both worlds. The way I'm going to do that is by talking first of all about general ideas, which don't need a lot of mathematics, and then I'll talk a little bit more about specific aspects of this theory. Now in the talk, what I try and do is have slides which have lots of details which those who are not interested in don't have to look, okay? So you can pretend that all these details are not there and just listen to what I say. Can I ask, can people see my cursor? No, that's unfortunate. Okay, well, I'll just have to tell you what you're supposed to look at if you're not interested in the details. So what I thought I'd do, partly because over the last 4 weeks I'm constantly being asked this question by people, by journalists, for example, is what is it that is supposed to be the problem about gravity and quantum mechanics? So I thought I'd start off by saying a little bit about that. This is a very important problem. It can't be overemphasized that right now, and for a long time now, all of the sciences have been founded on physics, and all of physics is founded on two theories, one of these being quantum mechanics and one being general relativity. This idea that all sciences should be founded on physics was unprecedented until general relativity and quantum mechanics were discovered. There's a famous remark made by Dirac at the end of the 1920s after the discovery of quantum mechanics. He said, well, chemistry has now become a sub-branch of physics. What did he mean by that? Well, he realized that with the discovery of quantum mechanics, everything you would ever want to know about the structure of nuclei, atoms, and molecules was suddenly accessible, and that chemistry was nothing but the employment of our understanding of these to understand chemistry. And then it became clear already in the 1950s that molecular biology was now going to become a sub-branch of chemistry. And since then, the understanding of living processes has followed. Of course, that's a long story, and it's by no means, we're only at the beginning of it. But this is what people mean when they say that all of these sciences depend on physics. Now you might ask, well, what about general relativity? What's that got to do with our ordinary everyday world? And the answer is not much, except that we're in the universe, and the term universe meant nothing until the discovery of general relativity. In fact, Einstein didn't even realize that he could start talking about the universe using his theory. And as many of you here know, one of the predictions of that theory, a very early prediction, was that the universe would be expanding, and he rejected this and tried to stop it by sticking an extra term in his equations. Since then, both quantum mechanics and general relativity have made outlandish predictions that the creators of these theories refused to believe. Quantum mechanics predicted things like entanglement, as articulated initially in the Einstein-Podolsky-Rosen paradox. Entanglement, spooky action at a distance is what Einstein called it. General relativity predicted singularities, the Big Bang, and so forth. The creators of these disciplines found these predictions so outlandish that they rejected them. But they were all correct. And the explanatory power of these theories has basically extended itself ever since. They're like magic wands. Everything they touch turns to gold. But then the problem is this. Quantum mechanics has been used to treat small objects, general relativity to treat the very large. We don't usually have to use them together. And the idea, or the problem, which is becoming more and more acute, is that they are incompatible. And as you will hear at this meeting, we are very close to bringing these two theories into confrontation with each other in experiment. So So I'm going to say a little bit about the views that people have about that. And I call the two views on this the high energy view and the low energy view. And as you'll discover, I'm more of a low energy person, particularly early in the morning. And I will be, if you like, pushing on behalf of the low energy view. But let me start with the high energy view because it is actually pretty much still the conventional view of all of this. So the high energy view is illustrated in this picture. The picture actually is sometimes called the royal road to quantum gravity by people in, for example, string theory. And they say, well, let's look at different energy scales. Physicists measure these energy scales in what they call electron volts. There are many other ways to measure them. It doesn't really matter how big they are. But what's useful to understand is that as we go up in energy, and that's going along this road towards this magic target here of the Planck energy, we also are going forward in time, because as time has gone on, physicists have been able, in experiments, to look at higher and higher energy processes. And you can see on the right, I show that around 1900, we were at roughly 10 kilo electron volts with the discovery of X-rays. The kind of X-rays that you experience, for example, when you go to the dentist are somewhat lower in energy, but this is really the energy scale that people had gotten to grips with around 1900. Actually, I put 2021 AD, but of course it's actually 2022, so that's the first misprint in this talk. You see how far we've gone. We've gone from 10 kilo electron volts to roughly 10 to the 5, 10 to the 6 giga electron volts, much higher in energy. It's taken 120 years to do that. Now, the people who believe in a high energy solution to the problem of quantum gravity, they want to go all the way to the Planck energy. And you see that if we follow this plot, it's going to take a long time to get there in experiments, roughly another 350 years. If you wanted to build an accelerator, which would accelerate particles to that energy, it would have to have a diameter of roughly 3,500 light years. So that's obviously not going to happen soon. There's only, in fact, one way to try and do experiments. And they're not experiments, they're observations, which you will be hearing about at this meeting, in order to investigate this. Let me emphasize a little more how big the problem is for this field. Now, you don't have to pay, this is where I start saying, these are the things that you don't have to look at if you don't care. You don't have to look at all these numbers. All you have to know is that the Planck energy that I'm talking about, the target of the high energy people, is really big. So if you take a single one Planck energy, an amount of energy equal to the Planck energy, and you inject it into a container containing 5 tons of water, you would raise that container from 0 centigrade to 100 centigrade. You'd boil it from if it was freezing. That's 5 tons of water. That's how big the Planck energy is. But in the experiments, or in the processes that we want to observe to see things happening at the Planck energy, we have to deposit that energy not into 5 tons of water. We have to deposit into a region which is a Planck length on a side. But the Planck length is 10 to the minus 35 meters. So we're depositing this colossal amount of energy into this incredibly small space. A cube, if you like, 10 to the minus 35 meters on a side. That involves energy densities that are 10 to the 45 higher than we've ever produced on Earth. So I think the point I'm trying to make here is that this is utterly beyond any conceivable experiment. The only viable testing ground that we know of is in the heart of black holes or very, very close to the beginning of the universe. So you'll be hearing more about that. That's the first problem. That's a problem for the high energy people to do with quantum mechanics and gravity. There's another problem, which is that if you actually try and do quantum gravity, theoretically, not in the lab, you find that we say that it's non-renormalizable. What does this mean? Well, I'll give a simple argument here for those who want to follow it. We all know that E equals mc squared. This is in the middle of the slide here. So we can say that m is basically E over c squared, but we can in quantum mechanics equate that to we can relate that to the wavelength of whatever it is that has this mass. And we see that the mass then goes like 1 over that wavelength, which means it's going like 1 over some distance, say the distance between two particles that are interacting via gravity. But that can be then worked out to give you a force between these two objects, and we find that that force goes like 1 over the 4th power of the distance between those objects. In other words, it blows up at short distances really fast. This is a very simple-minded way of explaining that gravity blows up at short distances. There's a very simple, intuitive way to think about this. And it's the following. In Einstein's theory, it's not mass that produces gravitational fields. It's actually what we call stress energy. And so if I create a strong gravitational field, what I'm actually doing is curving space-time, and there is a stress energy associated with that curvature, which means that gravity begets more gravity. If you produce strong curvature of space-time, that will create more. That'll be a source, if you like, for more gravitational field. So if you start bending space-time at very short distances, you're creating very high energy, which then creates, if you like, more gravity, and the whole thing blows up. Okay? So this is a problem that was clear a very long time ago in the subject, and it tells you that you're going to need some completely different kind of framework from conventional quantum field theory to attack quantum gravity, in other words, to combine the two. And there are points of view on this. So, oops, sorry, that shouldn't have happened. I'm quoting here Hiroshi Oguri from Caltech, who's a very well-known string theorist. So let me read that out. He said, "It is not well appreciated how hard it is to build a consistent theoretical framework to unify general relativity and quantum mechanics. Currently, superstring theory is the only credible theory to have achieved the unification." Now, I suspect that there are a number of people in this room who would disagree with that. They would disagree both that it's the only theory, and secondly, that it's even consistent. But that's a technical question. But this underlines the second problem of the high-energy theory, which is that it's very hard to find. Okay? Now, I'm going to, and again, you really don't want to look at all the technical stuff if you're not a physicist. But I want to describe the third problem very simply. It's this. Quantum mechanics tells us that we can superpose states. That I can, for example, envisage a state in which a particle is here and here simultaneously. Feynman made this very visual by talking about the way in which an object could go from point A to point B, following multiple paths at the same time. So you see at the top here, what's essentially a famous experiment, the two-path experiment. I imagine an object propagating from some initial point, which is the blue circle, but we're supposed to be able to tell the difference between whether it goes along one path or the other, which is why I'm showing an orange and an apple. And there's a very famous experiment done by Cavendish, and elaborated since then, where he tries to look where this object is by detecting its gravitational field. So the gravitational field will exert a force on some other object, and you see here we've got a kind of a dumbbell hanging on a thread, and that will rotate depending on the force that it feels. So it can detect along which path this object goes. Now in quantum mechanics, it can go along both paths simultaneously, which then tells us that we'll be putting our measuring system into a superposition of two different outcomes, which tell us which path it went along. And the bottom line here is that each of these two possible evolutions of this mass is associated with a different space-time, because the mass distorts space-time and therefore changes it, the space-time around it. And if it goes on one path, that distortion goes one way. If it goes along another path, the distortion goes another way. In other words, if we're going to talk about quantum gravity, we have to, never mind really high energies, just in our ordinary everyday world, we have to imagine superposing space-times. But this creates problems. Actually, all this jargon here on the slide, for those who are interested, is taken out of Bob Wald's well-known book. But the bottom line here is that you could have a situation in which, in one of those branches of that superposition, event A causes event B. In another branch, event B causes event A. And in yet another branch, they have no causal connection whatsoever. That completely undermines physics. Okay? So that's our problem number 3, that superposing space-time leads to apparently meaningless results. And in particular, it screws up completely our understanding of causality, and it screws up conventional quantum field theory, because quantum fields have to be defined with some causal framework, as defined, for example, by commutation relations. So these are 3 reasons why people are really worried and have been puzzling for a long time about how to unify these 2 understandings of nature. And the reason why this is really important, of course, is that these 2 theories underlie essentially everything in science. And so it's not good if they don't agree with each other. As I said before, for a long time we've been able to live with this because they are addressing different regimes. On the one hand, the very large, on the other hand, the small. But as you'll hear in some talks, that is not going to last much longer. Okay. Let me say a little bit more about this, but I'm not going to, I think I'll probably be running out of time. So I'm therefore adopting the low energy road, if you like, to trying to deal with this problem. So the idea is that people who look at the Planck scale are looking in the wrong place. Let me just remind people that it's not recently that we've been having problems understanding quantum mechanics. This has been going on for a long time, and in fact, many of the founders of quantum mechanics rejected it later on. Let me just very briefly remind you why that is. One is that we're supposed to describe nature, physical objects, by a thing called a state vector or a wave function, which, as I said before, can be in multiple different elements. It can have multiple different branches, if you like, of that wave function at a given time. So then people will say, well, what is this state vector? Is it a real physical object? That is something that most physicists would have a hard time with, because this physical object can change instantly in different places. And so this is the famous EPR paradox. So they say, well, it just represents our information about the universe. It's not a fundamental object, it just represents our information. This is a common point of view that you'll find. The problem is that different observers have different information. And we're apparently losing all reference to the physical world here if we're only talking about information. In fact, we end up with what seems to be a completely anthropocentric point of view on what our job is as physicists. It's not to talk about the world, it's to talk about our information. And this almost seems like a throwback to medieval times. So it's regarded by many physicists as a rather aggressive way of doing things. Problem is, of course, that it works. And this is, for most people, been good enough. But as I said, we'll be finding out in the next few years if it always works. And this is where one pushes quantum mechanics to larger and larger scales, so-called macroscopic quantum phenomena. Now, some people argue that we've already checked out quantum mechanics at the macroscopic scale. There's been a rather interesting debate going on for the last few years between, on the one hand, Tony Leggett, who's responsible for a lot of the theory, and Birgitta Worley, who is here and who is, by the way, also on the board of the Quantum Gravity Society. So it's been argued that actually we have seen macroscopic quantum phenomena, but when you come to define what you mean by macroscopic, it turns out that it's not quite so simple. And as I'm hoping Birgitta will tell us tomorrow, in fact, the degree of what is called sometimes macroscopicity in experiments is actually very low. So I'm actually taking here, on the bottom here, I'm showing you a figure which is delta N total, which is essentially a measure of, on the atomic scale, just how macroscopic some of these states are that people have looked at. And it's actually not macroscopic at all. These numbers are representing, if you like, the change in state of only a few hundred or a few thousand atoms. That's not macroscopic. Moreover, these experiments don't test what we call mass superpositions. They're not looking at superpositions where a mass is in different places, which of course would create real gravitational problems, as I already explained. They're just talking about, currents being in superpositions, and there's no mass displacement on that, and therefore no gravitational effect involved at all. So, conclusion, how macroscopic is quantum mechanics? Answer, in the lab, we've never shown macroscopic behavior beyond microscopic. And as was pointed out by Tony Leggett himself, phenomena like Bose condensation do not constitute macroscopic quantum phenomena. So when people extrapolate quantum mechanics and discuss the entire universe, as Slava will tell us, they're making a huge extrapolation, really huge. It's going from a few thousand particles to the universe, and that has never been tested. So let me give you a little bit of history on this low-energy road. It was really Feynman that first pointed out that one should think about this. He said, look, I would like to suggest that it is possible that quantum mechanics fails at large distances and for large objects. And he pointed out already two things. One was that if this happened, it would happen for objects whose mass was of order the Planck mass, corresponding to some 10 to the 18 particles. As you'll hear from Marcus, we're already at 10 to the 12 particles. And that leads to his second remark, which was, and this was made in 1957, there's no way we can check this possibility out because there are no experiments. And again, as I'm saying, that situation is now changing. A little bit more history, again, ignore the details. A lot of people have tried to put together a theory that cures these problems. The one that I like best is by Kibble in the late 70s, where he tried to incorporate gravitation as a mechanism for creating a nonlinear quantum mechanics. The conclusion he came to was that he couldn't make a consistent theory using the conventional framework of quantum mechanics, Hilbert space, operators, measurements, and so forth. And other people, notably Joe Polchinski and Nicolas Gisin, showed that, in fact, these efforts would lead to superluminal propagation, signals traveling faster than light, which was regarded as being fatal. Roger Penrose has been trying to do different things. He's been basically making dimensional arguments involving gravitational effects for a superposition, and has argued that there would be some kind of decoherence or dephasing between different branches which could be observed experimentally. But as he himself has emphasized, this is not a theory. He says, none of the considerations of the present paper give any clear indication of the mathematical nature of the theory that would be required. Okay. So I've probably left myself almost no time here. Let's see. I did want to get across the basic message. 7 minutes, okay, thank you. Basically what happened was that I got into a long discussion with Joe Polchinski back in 2010 about all of this, and told him what I thought should be done. And to my astonishment, he told me that I should publish it. And that's how I got into this game, because before then I was basically a condensed matter theorist. And so he pushed me very hard to do that, and so I did the next year. And then I was contacted by Andrei Barvinsky in Moscow, who unfortunately couldn't come because of political events that we all know about. But he has a very rigorous approach to these questions. And he basically helped me rewrite the theory in a somewhat different form. And then more recently, a student of mine, now a postdoc in Caltech, that's Jordan, Wilson Giroux, added some really interesting and important insights into the formalism. And I don't have time to explain all of that now, I just want to give you a very simple picture of what's going on. So, one of the problems, as far as I could tell, with the approaches of people like Kibble and Penrose was that they always tried to adopt a wave function start off. They said, let's start with wave functions, state vectors, and so forth. Kibble himself remarks that this basically leads to disaster. Polchinski made the same remarks about the attempt of Steven Weinberg to do the same. You end up with a Schrödinger equation which is nonlinear and which has all of these problems associated with it. But it seems to me there's another way to set things up, which is using the paths that were first introduced by Feynman, and then ask what would happen, or whether or not there's a way out of this impasse when you introduce gravity. And I'm just going to introduce you to a very simple thought experiment here. Imagine on the left that we have some single object, but it's traveling along two different paths, and it's interacting with some source of gravitation. Now, there will be, one will describe this in path integral language in a certain way, and it doesn't matter how you do it. But the next question you want to ask is, in a path integral formulation, is this distinguishable from a quite different thing where you have two different objects traveling along and interacting with this source? And the answer is no, because the only thing that enters into here is the stress energy of the system, and it's colorblind. It doesn't care what the particles are made of. All it cares about is what the stress energy is. And so, in fact, there seems to be no way that gravity can distinguish these two situations. One where you're having a single object with multiple paths, the other where you've got two objects with single paths. But if that's the case, then that indicates that there should be a gravitational interaction between paths in a path integral. So on the left, on the left at the bottom, I show you what conventional quantum mechanics says about the description of the motion of an object between point 1 and point 2. It says that along each path, this object can emit gravitons. It's a source of gravitational field. But because conventional quantum mechanics sums over paths, there is no interaction between these paths via gravity. On the other hand, in the CWL theory, the correlated worldline theory, there must be such interactions. You have no choice. And moreover, you have no choice about what the couplings are either. And this actually determines the form of the theory. And as I said, Andrei Barvinsky and I, had a lot of fun trying to work out precisely how this theory should be formulated mathematically. And Andrei did something even more important. So I'm not even going to discuss these slides because they're the formalism that we came up with, along with Jordan later. But what I am going to do is, let's see, so I'm going to jump over a lot of these slides because I have no time. Oh, sorry, that's going too far. What I wanted to do was explain, yes, here it is. One of the things that Andrei was able to establish about this theory, which I thought was very interesting and is shown at the top of this slide, is that it was consistent. It was internally consistent. So it had a consistent classical limit. If you switched off quantum mechanics, then it went to classical Einstein relativity. But you could also expand about that in powers of either h bar, the quantum Planck's constant, or something related to it, which is the Planck length. And those expansions were well-behaved and consistent. Moreover, all conservation laws were obeyed. So all Ward identities, including the Ward identities associated with diffeomorphisms, were obeyed. And finally, something that Jordan and I realized is that the theory is renormalizable, perturbatively renormalizable. So my response to the string theorists is no, superstring theory is not the only consistent theory. As I said, Andrei and I had a lot of fun working this out. I'm not going to discuss all the details because there isn't time, and I suspect it's not right for the audience, but Jordan and I worked out some thought experiments. Now let me get to this slide. Starting a few years ago, we formed a group that we called the G5 group, which involves myself, Bill Unruh, Yanbei Chen originally, and various other people have joined in. And Yanbei forced me to think about experiments. Ever since we started talking about this, he has never let up on the fact that we have to think about experimental tests of this theory. And so we have all these meetings. One of these recent ones involved Rana Adhikari, who very sneakily took a screenshot of us while we were all talking by Zoom about experiments. And this picture is to remind me of what we were talking about. A question that was raised by Bill a couple of years ago now was, how do you know that LIGO hasn't already shown this theory to be wrong? The argument was that the mirror in LIGO is supposed to be itself in a quantum state. It's supposed to be describable by a quantum state, because otherwise you would not be able to entangle the ingoing and outgoing photon beams in the experiment. Now, I remember that both Yanbei and Marcus jumped on Bill for this and said, no, that's not that's not the regime that they're operating in. And this has led to endless discussions ever since about this question. And it's also led to all sorts of interesting ideas about how to check the theory experimentally, which you'll hear about. I just want to mention one subtlety, and I'm just going to mention it, and that'll be the end of the talk. So I've said to you that the paths in a path integral now interact with each other. Actually, they attract each other, because this is gravitation. And that is actually the key to why a macroscopic object ultimately will behave classically in this theory. It's inside the theory. There's no assumption, extraneous assumption, as you have in conventional quantum mechanics, that macroscopic objects have to be classical. It actually happens inside the theory because these paths undergo what we call path bunching. They're attracted to each other, so they collapse on each other if the interaction is strong, which it will be if the object is massive. But the problem is that they have to get rid of the gravitational energy, which is coupling them. You have to siphon it out somehow. You understand, probably you've seen simulations of, say, a globular cluster, where you've got hundreds of thousands of stars all orbiting around each other. They're all attracting each other, but the globular cluster doesn't collapse, because in order to do so, it would have to get rid of all the gravitational kinetic energy. Same problem here. And so one of the things I've been looking at is the way in which this can happen. And it's sometimes not so easy. One way, of course, is that you have the system coupled to an environment. And that will certainly allow this energy to be taken out. Problem is that LIGO operates in a very, very high Q regime. It operates with the minimum possible dissipation. The Q factor in physics is telling you how long an object will ring after you've banged it. So a bell in a church may have a Q factor, a really good bell, a really big bell like they have in say, Austria. If you whack it, it may ring for a minute, and it's ringing at, say, a frequency of, 100 hertz. That's telling you that it's got a Q factor of 6,000. It's going to oscillate 6,000 times before the decay is obvious. The Q factor in a LIGO measurement might be 10 to the power 10, okay? So if you start the LIGO mirror oscillating, it'll go on for thousands and thousands of years. And the problem is that would be, in that regime, how long it would take to suck this out. So in other words, even though you've got this attraction between these paths, the problem is that it's going to take a long time. Of course, one obvious way to deal with that is you just reduce the Q factor in order to prepare the mirror. There are other ways that one can think about this, and certainly Yanbei has been thinking about them more than anyone. I think I will stop with the following remark made by Winston Churchill, which is that I will now pass with relief, or I will pass the baton, if you like, to people who are talking about experiments in this conference. Thank you.
Just to reassure everyone, there is one of the talks, unfortunately, cannot take place in the after coffee break. And
Yes,
that's why we had a little more time, and so therefore we did not rush too much.
Yeah, the fourth speaker this morning, Julio Para Martinez, discovered after he arrived here last night that he had COVID.
Okay, so many questions here. Maybe since you asked, let me ask. Yeah, please go ahead.
I watched a video in which you talked about the interaction between the two different paths, and you mentioned a graviton exchange between them. Was that slip of the tongue, or are you actually talking about a virtual or a particle exchange between the two paths?
Yes. So in conventional quantum gravity, if you try and do perturbation theory, that is to say you expand in powers of the strength of the interaction between matter and the gravitational space-time field, you find that you can write things in terms of what are called gravitons, which are like quantized versions of gravitational waves. In the same way, if one takes the electromagnetic field and you quantize it, you end up with photons. And you can draw diagrams where you show an electron going on and emitting a photon. So it's basically the same idea, and it comes from perturbation theory. So, but this raises, I think, perhaps the question you're asking, which is, if this theory causes a breakdown of quantum mechanics, why is it written in quantum mechanical language? And so I guess the idea is that this is showing that within the structure of quantum field theory, this mechanism ought to exist, and if so, it will cause a breakdown of the superposition principle. Now, the reason I showed the diagrams with the gravitons is because experiments will actually not be dealing with enormously massive objects. They'll be dealing with objects in the lab, so the gravitational effects are not enormously strong. This is one of the reasons why it's going to be quite difficult to see them. And they can be described by exchanges of gravitons under most circumstances.
So actually, I'd like to do two questions, if I'm allowed to. One is, in general relativity itself, there's this framework for testing how much it could deviate from general theory experiment, like the parameterized post-Newtonian expansion. Is there something in quantum mechanics that could be parameterized that could tell the deviation as you go to macroscopicity, as you called it?
Right. So I guess the question is, I mean, I'm a little puzzled because when we're dealing with macroscopic objects, we're dealing not with deviations from general relativity, but deviations from quantum mechanics.
I'm not worried about, I'm worried about deviations from quantum mechanics.
Oh, okay, good.
So is there a parameterized post-Bohrian or something where you look for deviations from quantum mechanics as you become more macroscopic?
Right. So this gets us into details. But essentially, the calculations that we've been using involve the strength of the interaction between the paths. Okay, so they are expansions in LP squared. But of course, as you get to more and more massive objects, you don't trust those perturbation expansions. Let me show you a slide here. Hang on. Well, I'll try and answer this question simply by showing you a thought experiment. This is the two-slit experiment. Okay, so as we all know, the two-slit experiment can be written as the amplitude for a particle to go from 1 to 2, that's the top right of this graph, can be written in terms of a phase interference term with an envelope function. So the question is, what happens when you add gravity? Well, in conventional gravity, nothing much, because all you do is renormalize the contribution of each path, and that's what's shown at the bottom here. And I'm showing the lowest terms in the two Feynman graphs at the bottom right. Okay. Now, of course, for a really massive object, you would have far more complex processes, and you would not want to analyze those using perturbation theory, and you would eventually end up doing it using Einstein's equations. But what happens in CWL theory? Well, as I was explaining, you now have gravitational interactions between the paths. And then the question is, well, how important are these? Well, you notice here that this, I now have a complex phase, and you see that in front of it here is essentially, I'm talking about the lowest order contribution, which is what will matter in a lab experiment, okay, the LP squared term. the Planck length squared term. But, and one can also talk about semi-classical gravity, but quite generally, and this was a contribution of Jordan, quite generally we can talk about the general form of the propagator for arbitrary strength. And then we find, and it takes a while to unpack these equations. I don't think I can give you an adequate answer here. But quite generally, you find that a particle propagates in the Einstein field produced by all paths, and that's independent of interaction strength. That's a non-perturbative statement. And that moreover, I think that says it all. To adequately discuss the formalism, to unpack this slide would take a while. Have I answered your question?
Not completely, not really, but.
Oh, sorry.
But let me.
The parameter is the Planck length.
Like the number of paths, right? This macroscopic.
Oh, sorry.
So is there some parameter which is not just Planck length, but also involves there's a large number of paths, some large macroscopic parameter.
Right. Okay, so the key point here is that you have to, as it were, incorporate an arbitrarily large number of paths. And then in the formalism that was first cooked up by myself and Andrei Barvinsky and then elaborated upon by Jordan. So what I want to show you here is the equation, more or less in the middle of this slide, which says that the propagator for an object to move from 1 to 2 is produced by taking the product over all multiple path propagators. So the little n here is the number of paths that are being incorporated, and we take the product over all possible numbers. So we multiply the single path by the 2 path, by the 3 path, by the 4 path, and so on, all the way up to infinity. And then there's this exponent here, which goes like 1 over the number of paths squared. And that's how you get the consistent answer. So no, the number of paths doesn't enter.
All right, so my second question is that the motivation that you gave about the interaction between the paths would also hold if these were 2 different charges, not just 2 different masses, they'd also potentially interact.
No,
Why not?
that's right. So these arguments, if you try and work them through, you find that there's no reason, that it is not the case that a pair of paths for a single electron is indistinguishable completely from 2 paths for 2 electrons in quantum field theory, okay? As far as, say, the electromagnetic field is concerned, and I'm now incorporating the spin properties and all the rest of it.
I don't see the difference between 2 charged particles and 2 masses if we're in small particle limit. You know, take 1 particle interacting by a Coulomb field and 1 particle interacting by a Newtonian potential. Why are they different?
Well, I think in the Newtonian limit you would have a problem, yes, but I'm talking quite generally. So you're asking what is the difference between the Coulomb interaction between 2 electrons, apart from the sign, of course, and the Newtonian interaction between 2 electrons? What makes
it different in a path integral between those 2 cases?
Right. So what I'm saying is that if you were just doing it in that that non-relativistic limit, then I guess there is no difference. But I'm not doing that. You're basically saying I can imagine in a non-relativistic path integral formulation, I can imagine having 2 electrons going along with a Coulomb interaction between them, and you're saying how can I distinguish that in path integral language between that situation and a situation where I have a single electron going along, with photons being exchanged between the paths of that single electron, which of course is not allowed in conventional QED. That's your question, right?
Yes.
And in non-relativistic electrodynamics, I guess the answer is there is no way of telling.